Hello everyone! In this video we will continue to examine topic 12.2 nuclear physics and finish up our discussion of the law of radioactive decay and the decay constant. So in the previous video we discussed sort of how dN dt equals negative lambda n, that fundamental radioactive decay relationship related to the fact that each individual nuclide has a fixed probability of decaying in any amount of time, gives us our equation for exponential decay. We looked at how that connects to the half-life, and we looked at how we might experimentally measure short half-lives using the activity. Okay, one final note here, which I forgot to mention, which is that, you have to be able to account as well for the background radiation. Okay, you want to be a little bit careful that when you're measuring the activity, there is background radiation occurring, and if you don't take it into account, you will measure the wrong values. This include cosmic rays, that is rays coming from the cosmos, high energy particles that travel through interstellar space, produced by one phenomenon or another in space. There are also radioactive isotopes in the Earth and the atmosphere, and leftover radioactivity, significant leftover radioactivity from nuclear testing. So in the 60s and 70s, there's a huge amount of nuclear testing done in the atmosphere in general, and that has long-term effects on the background level of radiation. Okay, so finally, there's one more mathematical technique that's really important to recognize for analyzing radioactive decay. For both n of t and the activity, okay, a of t equals dN dt of t, one can linearize the graph using a particular technique that is plotting the natural logarithm of the quantity versus the time. So let's see why that works. Take our equation for radioactive decay, n of t equals n naught e to the negative lambda t, and take the natural logarithm of both sides. That gives us the following relationship. Log of n, or log of n of t, really, is equal to negative lambda t. Notice we're applying some properties of logarithms here. So we take the log of this side, and the log of AB is equal to the log of A plus the log of B, so log of n naught plus the log of e to the negative lambda t, but of course the log of e, okay, is just the exponent to begin with. Okay, so log of e is 1, and that leaves us with negative lambda t plus log of n naught, which means that if we graph log of n versus t, the vertical intercept is then log of n naught. Okay, so we can get the original sample from that vertical intercept, and the slope is negative lambda, the decay constant. Okay, so by linearizing this relationship, we can read very clearly off a linear graph both n naught and lambda. And notice that that is true as well for the activity, because the activity is the same form. Okay. And one final thing to mention here, I probably should have said this earlier, but it's really important to recognize that when we solved this particular differential equation, what we were doing is we were asking the question, what is the equation for which when you take the time rate of change, it is just proportional to its own value? That's what this says. That's what it says. And exponential decay is the function that meets that requirement. So these are interchangeable things. This equation, all right, the equation that governs exponential decay, just is an equation that meets this particular property and is therefore a solution to this differential equation here.